The Lord is risen. Alleluia, alleluia. Indeed, he is risen. Alleluia, alleluia. Happy Star Wars Day 2. May the 4th be with you. All right, so let's start with this here. So any questions regarding the homework? No one? Wow. You were pretty good. Yeah, Madav?
For 15C, there was this type of radiation that, well, in the answers at least, that I don't think we were taught.
So it's they absorb a neutron, right? 15C? It absorbs a neutron?
Yeah.
Yeah. So what do you get here out of this? So what's the missing one?
I thought the answer was that it was an electron.
Okay, so let's look at this here. So the A number must be conserved. You have 134, 132. So it has to be 4, right? The A number for the resultant. And then the charge has to be correct. So 55 plus 0, 54. So it would be 1. It would be 1, really.
And I think that corresponds with
So
what
that would be hydrogen 4. Is that what it would be?
it said, that it was hydrogen.
Yeah, it's hydrogen. But hydrogen 4. I don't think there's any hydrogen 4 in nature. Yeah, you don't know. I guess it might be like a mistake from the textbook. I have no idea what this reaction is all about. Is that okay, Madav?
Yep.
Good. Yeah. So we have Marie Curie there. There's a movie coming up on Marie Curie very soon. Very soon. Okay. Please try to be here on time too. Okay. Mm-hmm. Okay. Any other questions? Radioactive decay. You got this all fine? Okay. All right. So let's go back to make sure that you have the document that I asked you to download. Yep. Hold on a second here. I did not put my Bluetooth. Hold on a second. Let me turn Bluetooth on here. No, not there yet. Takes a little while. Okay, so let's see. Are we there now? No. Bluetooth there. Okay, so let's try this again. Okay, hold on a second, guys. I have technical difficulties. So let's take this off here. So let's try this again. I don't see my screen mirroring. This is on the same, let me see if it's on the same network. Same network. Yes, it is. Yes, it is. All right. For some reason, it doesn't show me anything. So give me a second here. We'll get to the bottom of this. Okay, so let me start this again. Zoom back. Okay, that doesn't work well. Okay, let me try this here again. Okay, so let's do something radical here. Let's power it off and power it back on. So whenever you cannot find the problems, sometimes you just reboot it. So we'll see if it works. So I'll be back. Hold on a second. Forrest, I don't know if you have a problem with your connection. Come in, drop out, come in, drop out. Okay, let's see here. So that should work. There we go. All right, so back in business. Okay, so let's put this here. Okay, so today we're gonna start like talking about electricity. So this is a unit on electricity and magnetism. So the first one here is gonna be, of course, electricity. Some of it will be like a review of what you've learned, or what you failed to learn, what you should have learned in grade 9. For some of you, well, those that I had, those students I had in grade 9 2 years ago. So I think Jason, Sean, Timothy, who else? Luke. You're gonna see like some of those things here. You've seen this already in grade 9. Okay, so let's start with this. So hopefully you have this in front of you. Okay, so quantity of charge. So you know that we have like two types: elementary charge. Well, two types, yeah. So a proton that is positive, and electron that is negative, and both carries the same amount of charge, but opposite in sign. So the charge carried by a proton or an electron, the absolute value, the charge, is given by little letter e. That stands for electron, right? So little e. So for the electron, the e is negative, and for the proton, the e is positive. Now, you've all come across like mole, right? Everyone? Yeah, just give me like a shout here. You know what mole is, right? Yeah? Okay. All right. Only Madav is there. Only Madav says yes. Okay. So you use mole because when you're dealing with matter, there's millions and millions and millions and millions and millions of tiny particles. So you're not going to sort of write down like a super big number. So what you do here is you use like a big number to begin with, like a mole. This is a big quantity, 10 to the 23. And then you express like the number of atoms, tiny particles in terms of moles. All right. In the same way as for eggs, right? So instead of saying, well, go get 12 eggs, go get a dozen eggs, or go get like 3 dozen eggs. So 3 dozen eggs is 3 times 12, so 36 eggs, and so on. Okay, so in electricity, we have the same concept here. Electrons are very tiny particles, and when they move, when an object is charged, there's enormous amount of electrons that flows. There's enormous amount of electrons on a negatively charged objects. So this would be a very big number. So in order to sort of manage this, we start with a big quantity, and this quantity here is called the Coulomb. All right. So 1 coulomb corresponds to the charge carried by 6.24 times 10 to the 18 elementary charges. All right. So as I said, the concept of coulomb is analogous to that of mole in chemistry. Now, the symbol for quantity of charge, it's Q, because it says quantity of charge. So Q, quantity of charge. Not to be, sometimes it's a capital Q, sometimes it's a lowercase q. In any case, usually it's not confused with, I know it's the same symbol as heat, right? But usually from the context, you understand like which one is which, all right? All right, so the total charge an object has will be equal to the total number of elementary charge. Now, this is not exactly correct here, but just bear with me. Okay, so when you have a, so let me go back to grade 9 here. In grade 9, you talk about static electricity. Now, static electricity, it's when the electrons on the move and then eventually come to a stop, eventually come to what we call an equilibrium position. Now, when an object is positively charged, what does that mean in terms of elementary particles? So anyone here, if you don't answer, I'm gonna sort of choose because you're very quiet. So what does it mean here when an object is positively charged? Positively charged. Yes, Eric, you.
It has more protons than electrons.
No,
it has more protons than electrons.
The electrons. Okay. Now I want you sort of thinking the other way around here. I want you to think that an object is positively charged when it has less electrons than protons. Okay. So when we deal about static electricity, we're not doing nuclear reactions. So the protons, the number of proton neutrons in nucleus will stay the same. Right? It's only the number of electrons that will sort of change. So an object is positively charged when there's less electron than there are protons. So what we say that there's a deficit of electrons, okay, a lacking of electrons. When an object is negatively charged, in contrast, there's more electron than protons. So there is a surplus of electrons, all right? Okay, now, you've learned also in grade 9 the way to charge an object. There were like 3 ways. I'm not going to go over this in great details. It's not really the focus on grade 11, but you sort of may remember the first way to charge an object is by rubbing, right? So you rub, and then some materials have a greater affinity, greater liking for electron than others. So when you rub them, like one material might sort of give us some of its electrons to the other object. And as a result, the object that gains electrons becomes negatively charged, and the object that has given off like the electrons have become positively charged. So that was one way. The other way was like by charging by contact. So contact, you start with a neutral object, you have a charged object, make contact, and some of those electrons, if this is negatively charged, some of the electron will go on the neutral object, or if this is positive, some of the electron from the neutral object will go to the positive object in such a way that like neutral object will become charged. And the third one was by induction, right? So charging by induction, that involved like a grounding wire, if you may remember. But whenever you see the induction, it means to cause something to happen without touching, okay? So once again, I'm not gonna sort of go too much into details. Yes, Max.
So when you have like
I cannot hear you. Like just go closer to your mic or.
Hello.
Yeah, Max.
Is that better?
Yeah.
Okay. So when you have like a charged object, and you want to take when you have a negatively charged object and you want to like put it to a neutral object. So as you're moving it towards the neutral object, would some like electrons be lost into the air?
Well, yeah, some of it, some of it like will maybe lost to the air, but most likely, if it's a metal, if you want to neutralize like a charged object, what you do is you ground it. So you make sure that you have a connection between the object and the earth. And then what happens here is that if the object is positively charged, the earth will supply electrons to neutralize this. If the object is negatively charged, the excess electron will go to the ground. Okay, so that's how
okay.
you neutralize.
All right.
Okay, it's not exactly neutralized, but I'm not going to go over this. Okay, good. So as it says here, like, so if you want to know the total charge, it's going to be the total number of elementary charge time the charge carried by an elementary charge, a proton or a neutrons. Now, to be very, very technical here, this is how it goes here. Okay, so let's say here, whoops. Well, it's frozen. Okay, hold on. Not very lucky today. Okay, so let me sort of check here if frozen. Okay, maybe go back. All right, so let me stop sharing here. Sorry, guys. All right, so let me check. All right, so perhaps let's go with setting. Bluetooth, it's on, not connected. Why is it not connected? All right, so let me connect my Apple Pencil here. I don't know why. Okay, so it's connected. Let's go back to this. Yes, okay, good. Back in business. All right, so let me share. Okay. Actually, when I rebooted the iPad, I guess disconnected. Okay, so the real formula here will be as such here. So n plus, no, let me put this here. So n plus is the number of protons, and n minus is the number of electrons. So the real charge here will be this. Okay, so E here, so I put it in absolute value here. All right, so if there's more protons than electrons, so this subtraction here will give me something positive. If there's more electron than protons, then this equation will give me something negative, and it'll be like exactly correct here. Okay, usually it's always in electricity here. Well, not usually, but anyway, in current electricity, it's always electrons. So n here will sort of correspond to the number of electrons, okay? All right, but whenever you use this, don't use the sign, okay? So when we're doing like electricity here, current electricity, you don't really have to use the sign. Okay, so I'm not gonna do like well, I'll do a sample problem in a second. Okay, so as I said here, Coulomb is the equivalent of mole. It's a big quantity. So let's put like the dozen. A dozen eggs correspond to 12 eggs. Now, if I ask you, how much is one egg in terms of a dozen? Well, one egg corresponds to 1/12 of a dozen, right? Well, the same thing happens here. So if an elementary charge, if 1 Coulomb correspond to 6.24 times 10 to the 18, let's say, protons, or 10 to 18 electrons, how much is the charge of one proton or 1 electrons in terms of Coulomb? Well, you just do the exact same thing. You just divide. So you could take this here. This is 1 here. You just divide by 1 divided by 6.24 times 10 to the 18. And what you get is this. All right. So since 1 Coulomb is correspond to this much charge, if you bring this on the other side, that gives you the elementary charge on a electron or a proton in terms of coulomb. So it's a 1.6 times 10 to the minus 19 coulomb. Okay, so it says here, see examples 1. I don't know. I don't think you have the example. Do you have the example with you? Do you have this at the last page or no? No, I didn't put it. Okay, well, it's okay. We'll just do an example here. All right, so let's do a little example. So example 1. Yeah, it's a little bit laggy here. We're gonna get there. It's gonna change. There we go. Example 1. Very good. Okay, so let's say here. Okay, so fine. Okay, so find the number of electrons. Number of electrons that go by. Find the number of electrons that go by if a charge of, let's say, 4 coulomb goes through a filament of a light bulb. Right, so in little light bulb here, you have what we call a little filament here. And usually it's made of tungsten because tungsten has a very high melting point. So it produces a lot of heat. So you don't want to melt your filament, your little filament of metal. So let's say here there's 4 coulombs of electrons. In electricity, so what moves is, of course, the electrons. Not all the electrons, the valence electron for the most part, right? So here we have 4 coulomb of charge that goes through a filament of a light bulb. And we want to find how many electrons correspond to, right? All right, so this could not be like any easier here. So what do we have here? We have Q. And then what are you looking for here? You're looking for N. You're looking for the number of electrons, all right? Well, of course, you're going to use the formula here. And you're just going to isolate for the number of electron, right, that goes through. And then, so you have 4 coulomb divided by 1.6 times 10 to the minus 19 coulomb per electrons. And then that will sort of give you like how many electrons go through. So I know that this one here will be like times 10 to the 19. If I bring this up, and 4 divided by 1.6 is going to be close to 2 point something. So let's see here, 4 divided by 1.6. So you got 2.5. There you go. So, and this is very typical here. So you got like that many electrons, so 10 to 19 electron that goes through a filament of a light bulb at a given point, right? You have like 4 coulomb of charge going through, and then you have, so if you have 4 coulomb going through a filament, you have that many electrons. Yes.
Sir, so you said N equals to 2.5 times 10 to the power of 19 E minus, and then I don't know what that says, 1s?
Yeah, it's electrons.
Oh, okay.
Just the plural.
Oh, okay, gotcha.
It is. Okay. All right. So let's go back to one is good there. Okay. Okay, I'm going to go back here. All right. So let's do a review of what you learned in elementary school. So in grade 9, you know that like charges, of course, repel. This is laggy. I can see myself here. Like charges repel, and unlike charges attract, right? Okay. So now we're going to sort of consider like two objects that are charged, and the amount of charge on it will be Q1, okay, and it will be Q2. A French physicist by the name of Coulomb tried to sort of figure out like the nature of the electrical force as a function of how much charge, and also as the separation distance between the charge. And when you notice here, notice this. You notice that the electrical force, the magnitude electrical force, is proportional to the charge of each, right? So if we keep like Q2 and the separation distance the same, if we increase double the charge of Q1, the force will be also double, and so on and so on. And then you realize also, you notice also that the electrical force is inversely proportional to separation distance squared. All right, so inversely proportional. So you can combine all those proportionality relationship, provided that you put a constant proportionality in front, and the constant proportionality is called K. Finally, a K. But it's not the same as Planck constant though, all right? All right, so the constant proportionality is called the Coulomb's constant. Now, notice here that this looks like pretty much like the same form as the gravitational force. Remember? Gravitational force? You don't have to write this down here, but remember here, gravitational force was this, right? So it has the same behavior. All right, and this is something that we're going to sort of make use of, this analogy, because it's really, really hard sometimes to understand electricity because you don't see those electrons. They're very, very tiny. So very often we're going to sort of try to understand electrical concepts by referring to gravity. So as a whole here, mass is to gravity what charge is to electricity. Okay, so that's the analogy here. Okay, that's the analogy. There are main differences. The main difference, of course, is that gravity is only attractive, whereas electricity, the electrical force can be either attractive or repulsive. So that's a very big difference between the two. Okay, so this formula here, we're going to sort of study this in greater details next year in grade 12. Okay, it's not really important at this stage. Okay. Now, the electrical force is another example of a force at a distance. So if you have two charges here in space, they don't need to be in contact to feel the electrical force. So it's the same thing as the gravitational force. Now, in order to sort of come around physicists to wrap their minds around objects exerting a force on each other without touching, they invented what is called like the field. Actually, it was Michael Faraday that came up with this idea of field. We've already talked about the gravitational field. That's the same idea, right? That's the exactly same idea. So once again, don't write this down, but you remember here. So you have a little mass here, right? And then you put the tiny mass right here, and then of course this tiny mass will have a gravitational pull, right? And then if you put it like a little bit like closer, the gravitational will be in the same direction towards the center, right? But a bit stronger. If I put it like a little bit like farther away, it's going to still be in the same direction, but it's going to be weaker. And remember here that if you leave like the mass to itself, it's going to follow this path here, and this was called the gravitational field lines. Remember this? Gravitational field lines? So gravitational field lines around a mass is like this. Okay, whoops, it's not very good here. So gravitational, oops. So gravitational field lines. Well, you have this exact same thing happening for electrical forces here, okay? So let's look at this diagram here. This is very important. Here you have a negatively charged object. Around any charge, there's what we say an electrical field that is being set up. How do you map out this electrical field? Well, you map out this electrical field the same way as you did for a gravitational field. You, instead of putting a little mass at a certain location and inquire about the direction and magnitude of the force, what you do here is you use what is called a test charge. And the test charge is always positive by definition. So it's right here, the test charge, right here, a positive test charge. So very, very tiny. A test charge is always positive by definition. It's very, very, very small because you want to sample like a point in space. And what you do is you put it at a location. So like here, like for instance, right here, put it at a location. You measure like the electrical force. And of course, since the test charge is positive and this is a negative charge here, there's an attraction. So the force of the electrical force will be towards the negatively charged object. So you take note of the magnitude of the force, direction of the force, and then you move it like perhaps like closer. Well, of course, the force will be in the same direction towards the center, but it'll be stronger. Why it'll be stronger? Because the separation distance is smaller. And as you decrease the separation distance, the electrical force is stronger, right? Because it's inversely proportional. And then you bring it like a little bit closer and so on. All right, so now if you take this tiny positive charge and you let it go, in which direction it will go? It will go like this in a line. And this is called an electrical field lines. And you can appreciate here that those electrical field lines, they're all radial, all coming. I'm showing here, but there's infinity of electrical field lines. So this is called the electrical field. Well, technically the electrical field is this, those little arrows here. These are called electrical field lines around a negative charge. Okay, so if I have like a positive charge here, test charge here, it will move in this direction, right? If I put a tiny positive charge here, left to itself, will move towards, and so on. So this is in electrical field lines around negative charge. All right, so this is how like physicists could understood how objects can exert a force on other objects without touching. So it's the interaction of their electrical field lines that generate the force. Okay. So in contrast here, oh, this is laggy. Okay, let me stop it. I'm gonna stop sharing here because it's too laggy. Let me share this again. And my computer is going like crazy, as usual. There we go, we're back. All right, so this is the electrical field lines around a positive charge. So the electrical field lines around a positive charge, if I were to put a tiny test charge here, remember, a test charge is always positive by definition. So if I were to put a tiny positive charge, you don't have to write this down here. If I were to put a tiny positive charge, it would feel a force, a repulsion, right? So away from the positive charge. And if I bring it like a little bit closer, it'll be in the same direction, but stronger and so on. And if I leave this test charge to itself, it will follow this path. So this is electrical field around a positive charge, positively charged object. This is just the opposite of an electrical field charge around a negative object. Now, if we had a positive charge plate, if this were like an infinitely long charge plate here, this is how the electrical field would look like. It will look all parallel, okay, away, right? So once again, it makes sense because if I were to put a tiny test charge, remember, test charge is always positive by definition. I repeat, test charge is always positive by definition. If I were to put a tiny, let me sort of do the plus first and do the circle after. All right, so if I were to put a positive charge here, it will feel a force of repulsion on either direction, all right? Now, this one is interesting here. A single charge is called a charge is called a pole, and single, we use the Greek word for single, which is mono. So these are called monopoles, a positive monopole and a negative monopole here. When we have two charge, this is called a di, Greek for two, dipole. So this is called an electrical dipole right here. And this is the electrical field lines that you would get around a dipole. So let's see here if it makes sense here. So if I had a positive charge right here, you don't have to write this once again. If I had a positive charge right here, what will happen here? We'll feel a electrical force from the positive, and it will feel an attractive force from the negative charge. So the net electrical force will be towards the negative charge. So if I let go of a tiny positive charge, it will move this way. So this is why the field lines is going from the positive to the negative. Now, what about here? Well, if I put a test charge right here, put a test charge right there, what will happen here? It will feel a repulsive force from the positive charge. It will also feel an attractive force from the negative charge. But since it's farther than the positive charge, the attraction will not be as strong, right? So the overall net electrical force on this will be definitely towards the left. So this is why if I put a positive charge here, it will be going away from the positive charge. You can sort of do the same analysis here, and you're going to sort of find out that the net electrical force on a test charge will be towards negative charge. Now, when you're here, it's kind of interesting here. So let's put that at the top here. When you're exactly at the top, what do you have? Well, first of all, your equidistance from the positive and from the negative. You're going to have an electrical force from the positive this way, and you're going to have an attractive force this way. And since it's the same charge, same amount of charge, and the same distance, so the magnitude of these two forces will be equal. Well, the net electrical force will be a vector addition of these two. So if you add this like vectorially, what you're going to find? You're going to find that there's a net electrical force going this way. So this is why here, right here, the direction of the electrical field is going this way. Now, what about this way? If you have put a tiny positive charge here, what are you going to have? Well, you're going to have an electrical charge, electro-repulsive force going that way, and you're going to have a negative charge going this way, a negative force going that way. And of course, since the distance is not the same, the repulsive force will be stronger than the attractive force. So if you add this vectorially, it's going to give you like something, right, roughly like this, right? So this is why at this location here, the electrical field is kind of bent. Is that okay? All right. So any questions? Questions here? All right. So I encourage you also to try to draw like a electrical field around two like charges, like two positive. That might be like interesting for you to find out. Okay. All right. So we're going to talk about field in greater details next year. All right. So okay. All right. There's a bit of space here. It's coming to you. The bit of space. It's coming. It's coming. It's going a bit laggy. There you go. It's going to stop. All right. So let's talk about current. Current is a flow of charge. All right. Does anyone remember from grade 9 what is the symbol for current? What's the symbol for the current? Timothy?
I.
Yeah, it was I. All right, so I'll put I here. I'll just erase this here. All right, so is current was I. So flow of charge. And the formula is pretty easy here. It's just the amount of charge over the time. Now, what's the unit for the current? Well, you notice here that unit for current, notice here that Q, the quantity of charge, is given in Coulomb, and this is given in seconds. So Coulomb per second, and Coulomb per second is called the ampere. All right, so it's Coulomb per second. So the symbol here is, of course, A. So A is Coulomb per second. Okay. So let's do example 2. I don't have space here, so I'll do it separate sheet here. All right, so example 2. So example 2. Find the current going through the previous bulb if 4 Coulomb goes by in 2 seconds. Okay, you're gonna see here, this is not like chapter 15 and a little bit like 16. You're gonna see it's really easy. It's just like, even if you don't understand, you know how to manipulate the formula, you'll be okay. All right. So a little bit later on where you need like really to understand what's happening. Okay, so it's pretty easy here. So Q is, of course, 4 Coulomb. The time here is 2 seconds. And then you're looking for the current. So current is just the amount of charge per flowing per second. So it'll give you like 4 Coulomb divided by 2 seconds. And that's going to give us 2 amps. So there's 2 amps of current going through this light bulb. And it's very typical. It's a typical value for the current going through, well, typical. Yeah, probably. It's probably about 1 amp, but if you have a very intense light bulb, it could draw like 2 amps of current. Okay. Good? Okay. So let's go back to this here. today you won't have any homework, okay? So it's just like listen and then continue tomorrow. And then tomorrow you'll have quite a few problems to do. But as I said, they're not like typically very, very hard. All right, so here, so we're gonna separate this in two parts. And then here, we're gonna have, whoops. Not bad, but could be better. All right, so we're gonna have two plates. And one will be positively charged, and one will be negatively charged. So it's two plates in space. Then we're gonna have a negative charge. Well, let's do a positive charge. Positive charge right here. Now, there is an electrical field between those two plates. Oh, there's something I forgot to mention here. Electrical field lines, they always start at positive charges, they always end at negative charges all the time, okay? They always start and they end at negative charge. Although I didn't show you like the electrical field for a two plates, it's going to be like this. So this is the electrical field. Between two plates. We suppose here that those plates are very, 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 very big, very large, okay? I mean, it's not exactly true. It's not exactly like this, but it's good enough. So this is the electrical field. All right, so if I had a positive charge here and I leave it there, left to itself, what will happen? Well, of course, it's going to feel a repulsive force from the positive plate, and it's going to feel an attractive force towards the negative plate. So the overall force will be in this direction, right? So there'll be an overall force, electrical force. Everyone is okay? All right. Now on this side, so the charge moves because there's an electrical field. Whenever there's an electrical field and I have like a charge, be it positive or negative, right? It will sort of, if it's not kept from moving, it's gonna move, all right? So if it starts from rest here, if I put like this tiny positive charge right at this location right there and let go, what happens here is gonna acquire speed. And as it acquires speed, of course, it gains kinetic energy. Well, this is very similar to this here, guys. So let's say here, this is the Earth. Now let's say here I have a mass. Well, if I take this mass here and let it go, what it's going to do, it's going to sort of drop towards the Earth, of course, because there's a gravitational pull. All right. And if I were to draw the gravitational field lines, of course, the gravitational field lines would look like this. Right? At the surface of the Earth, they're more or less parallel because like the Earth is enormous. Remember, the electrical field lines are going towards the center, but over a short area here, those lines from your perspective are more or less parallel, right? So here, this is the gravitational field lines, right? And of course, there will be a gravitational force. All right. So this is the analogy here. So the charge here moves because there's an electrical field. The mass here falls because there's a gravitational field around the Earth. Now, the mass acquires speed, so gains in kinetic energy. Same thing happens here. So the charge here gains kinetic energy. Now, remember here that the gravitational force is a conservative force. So we can replace the word done by gravity by a function called the gravitational potential energy, right? So remember here that when it falls, whatever gain or loss in gravitational potential energy, it's going to be offset by the opposite, right? So if there's a loss of gravitational potential energy here as it falls, it's offset by a gain in kinetic energy. So this is what we learned last 2 weeks or 3 weeks, right? Well, it so happens that the electrical force is also, I'll put like little asterisk here because it's not true what I'm saying, but anyway, that's okay. Well, it's true for static charges. Anyway, the electrical force is a conservative force. So what does that mean here? It means once again that the word now by electrical force can be replaced by a change or the negative of change in a potential energy function that we call the electrical potential energy. So the same thing happens here. It has this positive charge here, gains kinetic energy, it loses electrical potential energy. So potential energy is U, and of course, E stands for electrical potential energy. All right. So this is very, 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 this is the analogy here between the two. Okay. Now it takes it's still laggy. It takes a long time to move. I can see here that I moved mine, but on yours it's still not moving. Are you gonna move? Okay. I'm gonna stop sharing here, and I'm gonna share it again. There we go. All right. Now it comes to a little crust here of the lecture here. Yep, sorry guys. There you go. All right, so in electricity, what we do very often is we take the change in electrical potential energy and we divide by the charge, Q, right? And when we do this, we get what is called the change in electrical potential, the electrical potential, all right? It's akin to if we were to take like the gravitational potential energy and divide by the mass. You remember here, charges to electricity, what mass is to gravity, right? So, well, okay, hold on a second. Yeah, hold on. I'll just All right, sorry guys. Sorry. Okay, so we go back here. That's Zoom for you. Okay, so if we take like this, if we were to take this, all right, so delta U, you remember delta UG is mg times delta H. So if we were to take this and divide by m, what you would get this, all right? So G times the difference in height. Well, the difference in electrical potential is to electricity what difference in height is to gravity. That's the analogy here I want you to remember here, okay, to take home here. In the same ways that a mass left to itself will naturally fall from high height to low height, in the same way a positively charged object will move from a region what we call of high electrical potential to low electrical potential by itself. It means that there's no other forces, okay? So what does it mean here? It means this. It means that here in this region here, this is a region of high electric potential. And the symbol for electric potential is V, not U. There's a difference between U and V. And as you move towards the negative plate, it moves toward a region of low electric potential. Okay? So, in the same way as a mass moves from high height to low height, a positive charge left to itself will move from high electrical potential to low electrical potential. And the sample is V, and the unit is volt. So the unit of electrical potential is volt. Now, there's no, here, like if you were to do this here, would be like joule per kilogram, right? But we don't use this we don't use this quantity very much. This quantity here would be called the gravitational potential, not gravitational potential energy, gravitational potential, okay? All right, so the key point here, a positive charge left to itself moves from a point of higher electrical potential to a lower electrical potential in the same way as a mass left to itself moves from high height to low height. You remember I told you here that there's a major difference between the two. Gravitational force is only attractive. Electrical force is both attractive and negative. And this is where the analogy breaks down. So we're going to sort of, so if instead of having a positive charge, I have a negative charge, all right? So if I had a negative charge, what will happen here is that the electrical force, oh, I'm still on the electrical force will be this way. It will be repelled by the negative plate and attracted by the positive plate. What I want you to notice here is this. The negative charge goes from low to high. Left to itself, a negative charge will always go from low electrical potential to high electrical potential. Now, you don't have this with mass because gravity is only attractive. You don't have like a kind of stuff that when you put it like a certain distance from the earth here, it goes away, right? It moves from low height to high height. You don't have this because gravity is only attractive, okay? And so that's the next thing here is that the negative charge left to itself moves from a point of low electrical potential to high electrical potential by itself. And you don't have a similar, there's no anti-gravity, okay? All right. So the electrical potential is the equivalent of height for gravity or for pressure. We're going to sort of come back to this for water-based system, okay? All right, so that's what I want you to study. This is what I want you to know for today. As I said, there's no homework. Just review this if you want, and then tomorrow we'll just continue and we'll finish this. All right. So any questions? Any questions? No? Understand everything? Okay, so I'll see you like tomorrow then, guys, at 10:30. And yeah, so if you have questions, I'll just stay for 2 more minutes, but otherwise, I'll see you tomorrow. So happy Star Wars Day. May the 4th be with you. Happy Easter. Bye-bye, guys. See you tomorrow.
Bye.
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 Bye.